Let's talk about turning our North American 120 RMS 60 hertz signal into something usable to make a plug-in wall clock where we derive the clock and the clock signal to run our clock and the power supply to run various sensors of our fancy clock. So the first thing is let's look at the 60 hertz spectrum, and we have nothing at DC, and this is a pure sine wave, and so we get a 1 volt amplitude at 60 hertz. And since these are the CN constants, which implies a cosine, we're at minus 90. So the thing is this is what's coming in. If I were to do a low pass filter, and let me just draw one. Okay, this is a non-log, non-Bodhi pot low pass filter. There's no DC here to capture, right? So all we're going to get is an attenuated 60 hertz signal. We need to turn it into DC. Now we can use a half wave rectifier where we take our signal and do that. And we can see now if I do a low pass filter, right, I'm getting a DC component right here. Now a more efficient way, but more expensive in terms of parts, although maybe a power supply that isn't that's cleaner will make your electronics more reliable. So it all when we say cheap, cheap to buy, cheap to own, cheap to make, cheap to dispose of, it's all means different things to different people. Anyway, the full wave rectified, right, which mathematically we can just do by taking the absolute value. We're actually getting more DC, and the AC part is now at 120 hertz because this doubles the frequency, right? The other one kept the frequency the same. So in fact, these two amplitudes are separated. Now, just for fun, I did sine squared as a way to get some DC. Not quite sure how to do this without op amps, which you need a power supply to run the op amp. But interestingly, you still get the frequency doubling, but you get a one harmonic that you have to filter out as opposed to the others. Or if we go back here, there's other harmonics, and I only took 5 terms. All right, there's more to take, but these plotted out really nicely. So let's go to LT Spice and see what this looks like. So here, let me move that into the center. I just simulated the wall voltage of a 110, converted it from VRMS to VPeak, and yeah, there's no ground per se. It's just a positive. There's just a potential. Now, what I found out quite rapidly is that it's kind of hard to get this to work if you don't um, knock down the voltage somewhat. So let's just look at that for a second. Is that this is swinging quite a bit, and what I did is just to simulate a transformer, I just um, scaled it down rather than deal with um, a transformer. So the green signal here is actually, you can just think of that as a transformer step down the voltage. All right. There's other ways to do that, but um, I felt that was pretty efficient. So then it goes into a full wave rectifier, which um, I had to put a ground in the circuit, otherwise LT Spice wouldn't run. Really, you don't have that. It just takes the differential voltage across here. Then we go, this resistor and that capacitor make a low pass filter, and we can plot that out, which we call it DC full. And you can see that um, it's kind of it's rectifying it, but there's still a lot of peak to peak variation, even though the voltage is about 10 volts. So I thought, well, I'll just use a linear LDO regulator in gray, and that it actually starts to make a clean signal. Again, there's other power converters that would be more efficient, but for the time I had, this was pretty good. And then since we're already on power supplies, I just used a notch filter at 60 hertz and calculated the RLC, taking the voltage across the high and the low pass makes a notch, which then I fed into another one, another power supply, this one at 3.3 volts for the sensors. Now, how to get the clock. So rather than taking the clock from here, I decided to take the clock from DC full, where you can still see 120 hertz ripple here. And 120 hertz would actually be fine because you can just take care of that in your microcontroller, or just divide the signal by 2. It's not a big deal. We don't have to go back to the original 60 hertz. In this case, I used a high pass filter and then scaled it because it's still just using a blocking capacitor wasn't really giving me what I needed in terms of the clock. So I just scaled it down and then amplified it back up to get clock 1. Okay. Then I tried it a different way where I used a bandpass filter and then scaled that up to get clock 2. And they're slightly different, but really we're getting 120 hertz clock signal that can be used by the system, or even if the microcontroller has an internal clock, you can slave it to the external clock to make sure that it's synchronized. Because the power company spends a lot of time making sure that the power's in phase and doesn't drift, so that it's actually a pretty stable source for a clock signal. So that's the whole system. Some issues with it is I feel I'm using a lot of parts if I'm making a commercial thing, I mean a consumer product, and that you probably have to go even cheaper for everything. And yeah, maybe half wave rectifier. And there's nothing in here with a fuse or any kind of safety things. And yeah, the transformer, um, that's a lot of, standard transformer, that's a lot of copper wire. Maybe that would be too expensive, and we would have to step that down, maybe even with voltage division, uh, and just use higher values of resistors with a good power rating, and that could take it down. It's not, let's say, efficient, but it probably a lot cheaper. So really, the big takeaways is that we have a 60 hertz sine wave that we use a transformer to knock down the peak voltage. A full wave rectifier turns that pure sine into sine waves and DC, which then we use a low pass filter to get the DC, and then we use a notch filter to get rid of any 60 hertz hum. And then for the clock, we one way was a high pass filter that got rid of the DC part and then assumed there was uh, nothing else that needed to be amplified. I mean, nothing else that would be amplified into the clock signal. We also tried a bandpass filter that was selective to 120 hertz because this doubled the frequency. Just a quick look is that when I look at the full wave rectified, oh, okay, that we're at 120 hertz because instead of a sine wave, now we're getting like the absolute value. This should have been, pretty good review of how all the concepts of circuits and the Fourier expansions and how you can use all of that to tie your knowledge together and to actually create a design. And this took me about 90 minutes to put it together, um, just to give you an idea. Anyway, hope you enjoy.